You already know various formulas about points in the plane and straight lines. In particular, you had this one about slope. We can use that same information in combination with a theorem from geometry to get something new. Pythagoras' theorem gives a relationship for the lengths of the three sides of a right-angled triangle. Now let's see what that says about our 2 points, x1, y1 and x2, y2. We know the lengths of 2 sides of that triangle, just the change in x and the change in y. Let's calculate the third side. Use Pythagoras' theorem and the 2 lengths we just found. And then take square roots, put it all together, and we have a new formula that gives us the distance between 2 points. It may look hard, but it's really easy to use, because all we have to do is substitute our points into the formula. Does that present any problems? Not if we start by identifying x1, y1, x2, and y2, the coefficients of the points, and then carefully plug them into the right spots in the formula. That gives us what we see here. Then we just simplify the arithmetic, which gives us our answer for the distance, the square root of 65, or an irrational number slightly larger than 8. Of course, the distance formula is good for, guess what, distances, but it's also very good for describing circles, as well as several other graphs we're going to be seeing soon. Using the formula isn't very difficult, so let's plunge in and see if you can do this one on your own. Be careful with the negative signs. Come back as soon as you have an answer. First question, should I draw a picture? Well, it couldn't hurt, and it might help. So I do. How do I know which point comes first? It doesn't make any difference. I'll get the same answer either way. So I pick one, and then I substitute. I am very careful about that double negative. And I find that this one has a nice round answer. Very convenient. So that's very nice, but I mentioned circles, didn't I? What's all this got to do with circles? Well, how would you describe a circle? It's round, it has a center, a radius, but the important thing is that all the points x, y on the circle are the same fixed distance from the center. That fixed distance is r, the radius. Does that sound at all like a distance formula? You bet it does. And here's what we get when we substitute our 2 points into the formula. And of course, this works for every point xy on the circle because the distance is the same in every case. And that gives us the equation of the circle. Every point on the circle satisfies the equation, and no other point satisfies it. How does this equation work out in practice? Let's take a look. We have the numbers we need. All we have to do is substitute them into the formula. And of course, that's no trouble at all. We can leave the equation like that, or we can go ahead and simplify it, like this. That may not look much simpler, but it is. Later, we'll see how to do this same process backwards when we want to recognize circles and other kinds of graphs. Now, it's your turn. Work this one out. Then come back and we'll check your work. I substitute in the formula. Then notice what happens to the y part. Y minus 0 squared becomes a very simple y squared. Which might start you thinking about what will happen if the center of the circle is at the origin. What happens is that we have a much simpler kind of equation to cover this one special case. Now, what if someone gives you an equation like this and says, draw the graph for this equation? If you've been watching our examples closely, you'll recognize what this is immediately. Yep, it's a circle. What we want to do is match up the shape exactly with our formula so that we can find the center and the radius. As usual, that double negative in the y term is a booby trap. Watch out for it. Now we know it's a circle, we know the center, and we know the radius. So here's the graph. Often you'll start with an equation which isn't nearly as tidy as all that. This one's fairly messy and rather interesting. What is this thing? The squares tell us that it's not a straight line. If the coefficients of x squared and y squared are the same, there's a good chance it's a circle. Our best first step is to reduce those coefficients to 1 by dividing. Now we have to mangle the equation until it matches our standard equation for the circle. The magic ingredient here is the technique for completing the square, which you learned in quadratic equations. There's a whole module on it if you need to review. Completing the square. First, the x part. We divide the 4 in 4x by 2, and then square the answer, 2. To find the magic number. Then we complete the square on the x part by adding the magic number 4 to both sides. That lets us write the x part in the shape we need, x plus 2 squared. Next, the y part. We find the magic number like this. Negative 2 divided by 2 is negative 1. Negative 1 squared equals 1. So we complete the square by adding 1 to both sides. And then write that as a square, y minus 1 squared. That's it. We look at the result, and it matches our circle equation. With that equation in front of us, we can simply read off the values for a, b, and r, which tell us the center and radius of the circle. From that, we can graph the circle on the plane, if that's something we want to do. Considering that completing the square is at the heart of this process, you'll probably want to practice a few more problems to brush up on completing the square. It isn't hard, but you have to keep track of the different pieces you're working with. But before you head for your textbook, take a look at this one. You'll want to start by completing the squares. First, I want to complete the square for x. I get x minus 3 squared. Then I do the same thing for y. That gives me y plus 4 squared. And from there on, I have the data, and I can do what I want with it, including graphing the circle on the plane if I want to. Do some more of these right away and be sure you're really comfortable with completing the square. Good luck.